Hello, hello. Hi, welcome to yet another Pep Talk, a good old post-employment podcast. Today, it is freezing cold in my car, even though it's only 45 degrees outside. My hands are freezing. It's a Wednesday, and because it's a Wednesday, I went into the office. And normally on Wednesdays, I drive straight back to my house that I rent out, which is over an hour away, instead of going to my parents' place that is only 20-some minutes away. But I'm meeting up with a friend today at his place, which is at the halfway point, so I figured I'd record one of these. Anyway, today I wanted to talk about space and what is in it. And the motivation for talking about this stems from this morning, or really last night. I was pining over what to decorate my office space with, because I still don't have any, really any decorations in my office. Not that I have an office, but like my desk. And we have pinup boards at our desks. And while I was home, I found a star chart. Now, if you know what a star chart is, you know how cool they are. But a star chart is a little piece of, usually it's made of plastic and paper, is a little map that spins.
Head south on Bankers Way toward West Chesapeake Avenue, then turn left onto West Chesapeake Avenue.
Yeah. Also, by the way, I've realized from now going through the recordings that the car noise is pretty bad. You hear my blinker, and you hear me driving and revving, and you hear the GPS sometimes. So I tried using my wireless headset to record these, and I realized that it just sounds muffled, and you can't get all my intonation and all my vocal acuity. So I figured, why not? I'll just keep the car noise. It keeps me interested when I'm editing these. Anyway, so where was I saying? Oh yeah, star charts. Star charts are little circle things, and you spin the circle to reveal layers to it. And the bottommost layer has a cool, basically the night sky. It's a pattern.
In 600 feet at the traffic circle, take the third exit and stay on York Road.
It reveals to you what constellations and what stars are in the night sky on that particular night, which is cool. So it has a month setting and it has a day setting, and when you line those up with the time of day, which also matters, so it has a time of day, it's not a knob, but setting, you get the accurate night sky above you. And when I first picked it up, I was like, wait, but what
in
year
a quarter
do I
mile,
set it for?
turn left onto Fairmount Avenue.
And then I realized, oh wait, it's a star chart. It's an annual cycle. The year doesn't matter for the most part. So it actually does. For astronomy's sake, the year does matter a lot. But for a paper star chart that you get in a science kit when you're a kid, it doesn't matter that much. So I have that pinned up on my desk. I got a pin in the middle, and I got a pin on the point on what day it is. And it's, as you walk by, you can see exactly what the night sky
turn left onto Fairmount Avenue.
Or really the noonday sky, because I have it set for noon. I really should set to midnight or something. Probably. Let's see. Oh, I can make a left here. Sorry, I'm going a route I never did before. Because there is traffic on the other way home. But yeah, so that's the motivation for why I wanted to talk about space and the night sky, and also the fact that this is going to be a 40-minute drive. Not that I will fill all the time, but I might, because it's space I'm talking about, and I did study aerospace. Although I studied the engineering principles that let you survive in space, not what's actually up there.
In 600 feet, turn right onto Goucher Boulevard.
I'll try my best to fill the time and be interesting. But yeah, first thing
turn
first,
right onto Goucher Boulevard.
Let's talk about Earth, because we're in space. The planet itself, of course, is situated
in a quarter mile, turn left onto Providence Road.
From the sun. Third major planet from the sun. I'm not counting dwarf planets. But I will count Pluto as a planet, because I grew up learning Pluto was a planet by some old educational software I had on a CD-ROM way back in the day, and it taught me Pluto was a planet. So I still think it is. Ooh, it started snowing. Sorry, I'm driving, and I'm
Turn
not
left onto Providence
in
Road.
warp yet in the Millennium Falcon, but it's snowing. That's cool. And we're on a planet where we can see snow on planet Earth because we are in the Goldilocks zone, which means that we have both heating and cooling seasons.
Continue on Providence Road for half a mile.
Throughout it, which is cool. There are other planets in the solar system, or more so, I should say, moons of those planets that have snow. Although the snow is usually not water ice. I don't think it ever, as far as we can tell, it's not water ice. Like there's, is it Io? Or it might be Io. It one of Jupiter's moons that has ice volcanoes. I have a friend who, she works for NASA, and she studies ice volcanoes on whatever moon of Jupiter it is that has it. I think it's Io, but don't quote me on that. It might be... I'm mixing up my Kerbal Space Program moons with
in 1,000 feet,
moons.
use the right lane to take the I-695 East ramp to Essex.
That's okay. But anyway, so we are in a cool spot in the solar system as a planet where we have seasons. And that is not a typical thing for planets, generally speaking. Planets do have seasons. It's not a typical thing that their season range falls within habitable life range, at least as far as we know habitable life is. Like, most of the world lives between 0 and 100 degrees Fahrenheit.
Use the right lane to take the I-695 East ramp, then merge onto I-695 East.
Negative 15 Celsius to like 45 Celsius. Like, most of the world lives in that range. And the planet varies in that range, with the exception of a few extreme places. And that's where life lives, and that's cool. And the reason for that is a mix of our atmospheric composition, our distance from the sun, as well as our rotational period and orbital cycles. So, that being said, you get all these things that come together, and you get a planet that we can live on, which is cool. And we are in space, and we are shielded from the effects of space. Now, what are the effects of space, you might wonder? Maybe I should talk about that next. So, when you leave Earth, before you get to the moon, before you get to a planet, you have space. The final frontier. And while I will not relay to you the voyages of the Starship Enterprise, I will tell you that space is a deadly place. The closest analog we have to it is like deep sea exploration, which is actually the exact opposite. In space, you have multiple things that will kill you. Number one, lack of pressure. Pressure is force over area. On Earth, we have an atmosphere, and that atmosphere actually has mass to it, and there's gravity, which by, G1 times G2 times M, it's G, the gravitational constant of the universe, times mass 1 times mass 2 over the distance between their centers of masses squared is the force of gravity in whatever base units you want to use. So if you're using meters per second, that's what it is. So like the meters per second squared? Yeah, this is acceleration due to gravity. Hold on. Mass over area. I'm trying to remember what the constant is. I'm pretty sure that is the force between two objects, not the actual acceleration between them, because you have mass, and that would make sense. Anyway, the acceleration, which is worked into the A number, is 9.81 meters per second squared at Earth's surface, and that is determined by the mass of an arbitrarily small object and Earth, with the distance from the center of the Earth to the outer crust where we are at. And that's how you get gravitational acceleration on the surface. Now, if you go farther up, if you leave the atmosphere, and, well, if you just get farther up, that number goes down because the distance between the centers of masses increases. So, as you go higher in the atmosphere, there's less force, there's less pressure, because the stuff up there is attracted less to the Earth than stuff lower. There's also when that stuff's attracted, it's also pushing down on all the other stuff below it and above it that's attracted to it. So you get this concept of pressure of like, hey, I'm on the surface and the atmospheric pressure is about 100 kilopascals, or 1 atmosphere, which is easy units. And I feel that. But if I go higher up, that pressure decreases. Now, you might, when you think of Earth as a planet, or when you think of any planet, you might think that, the planets have a clear edge. Like when you see pictures of planets, like they have a cutoff of like, here's the atmosphere, and beyond the atmosphere is just straight up space. Well, that's not true. It's a gradient because of how forces and gravity works. There is not a pure cutoff for our planet's atmosphere to go into space. As you leave, there's less and less pressure, and there's less and less mass because there's less force of gravity, and you get to a point where molecules and atoms bouncing off the other molecules and atoms sends them enough energy to leave the gravitational pull of the planet. And when that happens, that stuff is lost to space. Now, for the most part, well, I don't say most part, but that doesn't happen to a point where we need to worry about it. Like, sure, our atmosphere is slowly being lost to space, but the pull of Earth is strong enough to hold almost all of it. It's just that there's a gradient, and there's not one clear, like, oh, this is space. Now, we have cutoffs that we have in our science journals and such, and our atmospheric tables that we, as people, call space, or can argue for space. So, like, if you're 80 miles above, like, some people say that's space. If you're 100 miles above the surface, some people say that is space. It, like, depends on who you talk to. But anyway, so the pressure decreases because you're getting farther and farther away from the gravitational pull of the Earth. Once you get into what is
in 2 miles, use the right 2 lanes to take exit 33 for I-95 south toward Baltimore.
Pretty much ceased. There is stuff in space in terms of, like, there's mass and there's particles floating around, but there's so few of them. And that's the other thing. Pressure doesn't require just gravity. Pressure also just requires volume. Like if you have a bottle and you blow into it, like you can pressurize the bottle. And that's because you're putting more mass in a fixed volume of space. Well, space as a whole is a fixed volume. I mean, it's expanding, but like it's not infinite. At least as far as modern science can tell, space is not infinite. Outer space is not infinite. I might refer to outer space as space, just to clarify. That might help. So outer space is not infinite. And while there is pressure up there because there is stuff floating around, there's so few things and there's so much volume in outer space that pressure is inconsequential for almost all intents and purposes. This means that one of the most deadly things in space is this pressure differential. Outer space is pressure differential. And that's simply the difference of pressures of things. So when I alluded to deep sea exploration as the most analog,
in a quarter mile, use the right 2 lanes to take exit 33 for I-95 south toward Baltimore. It's
the most analog because you have to deal with pressure differentials. So, in the deep sea, you have very high pressure, and the cabin where the humans are is the low pressure zone.
Use the right 2 lanes to take exit 33, then keep right at the fork.
In space, you have the low pressure zone is actually outer space.
Keep right at the fork.
And the high pressure zone is your capsule, or your cabin, or whatever you're in that's up there. So you have very similar design constraints in the sense of there's not really outside air to pull from. There's not really like food find up there, sure. It's hard to generate electricity sometimes in these situations to keep stuff alive. Like if you're in the shadow of a planet, you can't use solar panels for that period of time, so you have to consider like how big are my batteries, that kind of stuff. But also the pressure, how you design your hulls are very similar. One keeps pressure in, one keeps pressure out, but it's still a pressure vessel. And so the pressure differential space will kill you, because your body is made to operate in normal atmospheric pressures. This is a side tangent, but a cousin of mine, he used to work on a Navy submarine, and one day he was in the engine room at dry dock, and the test the sub, they do cabin pressurizations, which is they seal off the bulkhead doors, they make it airtight, whatever room they're trying to pressurize, and they pump a bunch of air in to check for leaks. And it's routine, it's normal, and you don't do it when people are in the room, because our bodies are not made to withstand pressures of different types. So it turns out it was an accident. There was like him and 5 guys in that room or something, and they pressurized the room to like 30 psi. Now, normal atmosphere is, if I remember correctly, about 22 psi, pounds per square inch. And they didn't keep it like that for long. They realized there were people inside, and they very quickly depressed it without hurting them for the most part. And let's see. What happened was the people he was working with got vertigo. They get nauseous. They're not used to the pressure difference. It like screaming headache. Like it's vertigo. My cousin, he got vertigo too, but his stuck around. Turns out he got a little cyst that popped up.
In half a mile, keep left at the fork to stay on I-95 South.
That caused too much pressure in his spinal column, which made him have vertigo. Now, the Navy fixed it. They paid for surgery, which would have been stupid amounts of money, and things are better now.
Keep left at the fork to stay on I-95 South.
No hard feelings. Anyway, but that thing was designed to hold pressure. And
continue on I-95 South
like
for 5 miles.
8-degree PSI difference is enough to screw us up, both above and below. So in space, you get lower pressure. And what that happens is your cells in your body start to, they burst a little bit. The vacuoles in your body that hold water or other things will start to expand, and then they'll burst through the cell walls. It also depends on how long you're out there. You'll flash freeze a little bit. I mean, it's not like you don't actually cool off that fast, like the movies show it, because there's not much stuff for your body to convey heat to in space. And also, you radiate heat at a rate, but it's not so much that you are going to instantly freeze to death. So what they show in movies of like people icing over, that happens, but it's not as fast. It's what will hurt you first is the pressure difference. So they, and by they I mean like people who write science fiction, but also have some groundings in reality. They say that if you are caught in space without a suit, you need to breathe out and exhale. And they are completely right. If you try and hold your breath in space, the pressure difference from your lungs to outer space will rip the air out of your lungs, and you will expand, and you just tear up your lungs. It won't be fun. It'll be very painful, and then you won't be able to breathe at all. Not that there's anything there to breathe, but the trick is actually to let all the air out of your lungs and collapse them as much as you can, so that they equalize as much as they can with the vacuum of space. Like the human body, it's kind of cool. We can survive a few minutes in outer space without dying if you do it right. If you do it wrong, you will die. And you're going to be unconscious almost instantly. You got about 10 seconds of consciousness, I think, because of how blood oxygen in your body is absorbed by your brain. The blood that's currently in your brain has about 10 seconds of efficacy before it runs out of oxygen, in those circumstances. And so you'll be conscious for the first 10 seconds, and then you'll pass out, and then you'll die happily. But if, let's say 3 minutes in, you did things properly, and your body is still there, like, people can resuscitate you, and hopefully you survive it. You might have nerve damage, but you survive it. Now, I want to talk about space and what's in it, but I feel like I'm getting hung up on the human factor side of space, because that's what I studied. I studied, like, life support, how to keep people alive, and I can talk about that all day long. And maybe I just will. I don't know. But I do want to talk about space and what's in it. So, pressure difference, I think I've hammered that point home. Radiation. Fun. Radiation. There's a ton of radiation in space. Who would have thought? The atmosphere blocks like 99% of ultraviolet radiation that we experience here on Earth. You think a sunburn's bad, like imagine that times 100, or imagine that 100 times faster.
In half a mile, use the second from the left lane to stay on I-95 South.
That's kind of what space is like. Now, I can get into the real technicals of this because I studied and had to for my capstone project, space radiation, because we were designing a capsule to keep people alive.
Use the second from the left lane to stay on I-95 South.
We called it Muscle One. It was a multi-use space station for servicing.
Keep right at the fork to stay on I-95 South. Continue on I-95 South for 4 miles.
And something else in low Earth orbit. Low Earth Lagrange point 1 orbit. Sorry, not low Earth. Lagrange point 1 orbit. Servicing, science. Yeah, I forgot. There's 3 S's. Anyway, so I was on the life support human factor side, so I kept people alive. That was the goal. Anyway. So, radiation is like, if you're outside a capsule, pressure will kill you. If you're inside a capsule, radiation will kill you first. If you're not properly shielded. So, radiation is hard to block. There's 2 types of radiation in space, not talking about the specific wavelengths, but more so like the types. There's galactic cosmic rays, GCS, and that's like the stuff in the background from supernovas going off, and just general like other spatial events that output tons of radiation and light. And what's interesting about GCSs is they are usually super ionized iron nuclei. So we're talking like iron nuclei with a plus 53 charge. Like all the electrons have been stripped from them, and they are ejected from
In 2 miles,
supernova.
take exit 52 for Maryland 295 South, Baltimore, Washington Parkway.
Near speeds of light speeds. And because they're moving so fast, the electrons can't hold on and keep up. That's not exactly why. There's also a lot of ionizing radiation, so that, rips stuff away. But it's a lot. And those iron nuclei will just pass through things.
GPS signal lost.
There's a cool, I don't want to call it experiment, but a cool test that the Apollo astronauts did when they were in their capsule. They would sit for like 5 to 10 minutes with their eyes closed, and they would count the number of like streaks that went across their eyes while their eyes were closed. And what those things were iron nuclei traveling at ludicrous speeds, shooting through their eyeballs and passing through harmlessly, for the most part. it's because they're moving so fast, they just go through things. Like, they don't hit stuff and stop. They just keep going. And they fit through the space between atoms. So there's a lot of that. That will kill you slowly over time. But not as fast as SPEs will. So SPEs stand for solar particle events. It's the radiation that comes directly from our sun itself, for the most part. So you've probably heard of solar flares. Solar flares are really bad SPEs that make it all the way down to Earth, and like we feel the radiation effects down here.
In a quarter mile, take exit 52 for Maryland 295 South, like, Baltimore, Washington Parkway.
You're not going to die or probably get cancer from SPEs while on Earth, but if you're caught in space, you most definitely will. Because we are shielded. Thank God for that. But it still is enough radiation though to mess with.
Take exit 52.
So you've probably heard of like the big doomsday. There's going to be a solar flare that shuts down the internet. Well, that could happen. That could actually happen.
Continue for 3/4 of a mile.
That's why it's always important to keep your electronics in a Faraday cage. Yay! Not everyone has a Faraday cage, though. And if you don't know what that is, it's simply just a wire cage that you run electricity through. And it generates a magnetic field. And the magnetic field captures and prevents radiation from entering it if it's designed right. Pretty cool. They're pretty simple too. But anyway, Faraday cages aside, radiation in space will kill you very quickly.
In a quarter mile, merge onto Maryland 295 South.
We had to design against SPEs. GCRs, you can't block. Unless you had like 10 feet of concrete, like you can't block a GCR. They're just too energized, too energetic, too fast. You can't really block them unless you go on the ground, which is actually why for space colonies on like Mars and the Moon, which we'll get to, they usually design them underground for long-term habitation. Short-term, you'll be fine. Relatively fine.
Continue on Maryland 295 South for 11 miles.
Long-term habitation, you need to block GCRs. Short-term, you block SPEs. Now, SPE are more like gamma radiation and like more traditional forms of what you think of when you think of radiation. And our bodies can only absorb so much of that. Now, the units for radiation that's often used in space, as well as on Earth and around like nuclear reactors, there's a lot. There's rads, which are a unit of radiation. There's gray, which is a unit of radiation absorption by tissue that is convertible to rads. And then there is one more that starts with an S, I think. That is basically just 100 rads. And I'm trying to remember exactly what it was called. But that's the units. Sieverts. Yep. And 1 millisievert is equivalent to 1 rad, I think. So maybe it's 1,000 to 1. I'm not sure. But millisieverts are also equivalent to like mellogray. And that kind of stuff. It's weird. They're all kind of like equal to each other, but they describe different effects. One is like pure radiation measurement. Another is like tissue effect radiation measurement. Because our tissues absorb different amounts of radiation, wouldn't you know? Like, or they're more susceptible. So like bones are really susceptible to radiation because the bones in your body make your blood. And when you screw up the blood making process, you screw up DNA and you screw up, your body's entire functions, all its functions. But like your skin is pretty resilient to radiation because it just sloughs off every 3 weeks anyway. Like it doesn't care if it dies for the most part. Or its DNA is screwed up. It's just gonna, gonna make dust anyway. Which is interesting. That's why sunburns you can heal from, but like, swallowing a piece of uranium, you're not. I don't know. That's more of a dosage problem, though. Anyway, radiation's fun. That will kill you. You can block it. You use You use a lot of hydrocarbons. Hydrogen's really good at blocking radiation, but it's really impractical to put hydrogen gas around you because it's not dense at all, and it's really hard to keep cooled, so you can't keep it liquid form, which is the densest that we can really get to practically, which is some spacecraft use liquid hydrogen as fuel. So the next best thing is water. Like, if you can store water, water's a great blocker because it's made of hydrogen and oxygen, and it can block stuff. Let's see, but it's not practical to surround your spacecraft in water either most of the time. So you have to be careful about that. So you got to use other things. Well, plastics are hydrocarbons. They're polymers. I took a class on polymers as well in college. Not that it's in my major, but for funsies, I took a materials engineering class on polymer creation. And polymers are hydrocarbons. They're hydrogen and carbon with a bunch of other stuff tacked in. And that kind of determines what the plastic makes and does, and how long the chains are. There's a lot to it. But yeah, so plastic is good at blocking radiation. It's not the best, but it's good. So spacecraft hulls are usually coated, or they're aluminum or other metals, titanium, and then they have a layer of plastic on the outside of them, and then they have something called a Whipple, typically, which blocks micrometeoroid impacts. Or it doesn't block it, it reduces their impact effectiveness. Because I also wanted to talk about things that will kill you in space will be micrometeoroids. Those are fun. So bullets travel fast, right? Micrometeoroids travel stupid fast. Orbital velocity. So once you got up to orbit, you've survived the radiation, you're surviving the pressure difference, you're in orbit now. Orbital velocity, to keep your orbit, you got to travel really fast. We're talking like miles per second, not miles per hour speeds. Kilometers per second, not kilometers per hour. You're going really fast. And I don't want to quote numbers here because it will depend on both the planetary body you're orbiting, as well as how high you want the orbit, or low, as well as if it has an atmosphere and you have drag to deal with. Like, there's a lot of factors that determine orbital velocity that you need to worry about, especially escape velocity. But just know that generally speaking, you have to go many like miles per second to maintain that. So you're not the only thing going many miles per second to orbit things. There's dust and debris and little rocks, and the remains of that one Chinese satellite they blew up and pissed off the world because of it. And those are all traveling around Earth or other planets at multiple miles per second, very fast. Now, if you get hit by one of those, well, you'll die. I'm just straight up. There's so much like kinetic energy, you're probably just going to die from that. But it will go through you because we're soft, we're squishy, we're fleshy. We're not hard like aluminum Whipple shells. And aluminum Whipple shells do their best at absorbing these impacts. They take the brunt of it, and then usually there's a net in between, a really fine fabric in between the outer aluminum shell and the inner hull shell in spacecraft, and that helps block the fragment. So a piece of little rock dust hits your craft. It goes through the first layer of aluminum because it's so fast, but it breaks up as it does that, and then the fabric catches the shards, so it doesn't go through the hull. That fabric is also usually used as thermal insulation as well, so as a multi-purpose MLI, or multi-layered insulation. It's made up of like at a minimum 18 layers of interwoven like fabric. I'm talking like nylon and Kapton and other sorts of stuff, and usually not adhesive, but like some bonding layers. It's really interesting. Like it's a blanket, but it's a space grade blanket. I don't know if you can buy this stuff aftermarket, but that'd be cool to see like a survival blanket made of MLI that is probably, it has Kevlar in it too. Like, that stuff could stop bullets and also keep you warm at night. So I'm curious to see what that would be, if you want to give me a Christmas gift. Yeah, so micrometeorites, they travel fast. They'll get you in space too. They're up in space. I really haven't talked about other celestial objects much. I'm just kind of talking about humans and how we relate to it, and that's okay. Because ultimately, this podcast is going to be heard by humans, not by the planet or moons. I don't know, I'm just talking now to talk. But, what else? So, oxygen, food, it's not up there. You got to bring it with you. What else is in space? Space is a vacuum. We talked about that. There's planets. Cool. There's the sun. Cool. There are nebula. They're nebulous. Nebula are cool. They're a collection of dust in space that make really cool clouds and refract light in interesting ways that make pretty space pictures. Thank you, Hubble, for looking at those. But yeah, nebula are simple. Nebula are just collections of gases in space. And normally gas is spread out, and nebula do spread out too. But they also have gravity, in a sense, because they have mass. So eventually you get enough little pockets of gas, and they kind of form up to make a bigger pocket of gas that just keeps growing as, mass enters the equation. Now, if
in 2 miles, take the Maryland 175 East exit toward Odenton.
Big enough, it will start to really collect on itself because of gravity, and you'll get something known as a star being born. Stars are cool. Stars are giant thermonuclear reactors that operate solely off of combustion and pressure. Maybe not fusion. Sorry, not combustion. Fusion and pressure and gravity. So, what a star is just a collection of mass that's not stable, and it gathers in on itself, and there's so much gravity and pressure over time that it causes nuclear fusion to happen, and fission, but mainly nuclear fusion. The fission effects are minor because there's not typically heavy metals to fission, to conduct fission on. Fission is breaking down big stuff to make energy. Fusion is putting together little stuff to make energy. And basically, stars do this ad nauseum until they die. And what makes a star die is when it can't do fusion anymore. And it can't do fusion anymore.
In half a mile, take the Maryland 175 East exit toward Odenton.
Combine it anymore, or it can't split it out anymore. And that thing is iron, the 53rd element on the periodic table. Iron is incredibly stable for some reason. That's why we use it as the basis of construction for much of the world.
In 1,000 feet, merge onto Maryland 175 West Jessup Road.
It's so stable, in fact, that when a fusion process gets to iron, so it'll fuse all the way up. It'll do 52 fusions ahead of time before it gets there.
In a quarter mile, use the left 2 lanes to turn left onto National Business Parkway.
Although I might skip some reactions, depending on, what's going on. It's so stable that it just straight up can't fuse. Or at least the conditions for it.
Use the left 2 lanes to turn left onto National Business Parkway.
In a star to fuse iron. And what that ends up happening is it stops the reaction once you fuse up to that. Well, cool. Reaction stops. Well, what happens to the star? You still have just as much mass there. You have energy, too. And it's super hot, and there's a lot of gravity and a lot of pressure. But you can't fuse, so you can't continue the process. So you just build up iron. And stars build up iron in their cores slowly over time. And when it gets to the critical point where the iron in the core is so intense, or so immense, and there's not enough fissionable or fusionable material left the reaction ceases and the star collapses in on itself. And the reason it collapses in is because it's hot and there's a lot of mass. And when it collapses in on itself, it can do a couple things. It can go supernova, which is a release of energy, which, it collapses in, it builds up energy, and it's like a spring, it lets it right back out, although it's a bit more nuanced than that. It can also form a black hole, if it's big enough, which is basically a collection of mass that is so intense that it traps even light from escaping it, which, if you remember my podcast on light doesn't really have mass that we can measure. I think it does, though, but we haven't really been able to measure the mass of a photon. But the fact that light can't escape it means that there's a force acting on the light, and if that's the case, then force acts on things with mass. But science can't explain it yet. We're still figuring black holes out. We know what they do, but we don't know how they work.
In 800 feet, at the traffic circle, take the third exit and stay on National Business Parkway.
Yeah. So, black holes are cool. They can make that. Or it can make a dwarf star, which is fun. And usually the result of supernova make dwarf stars as well. What a dwarf star is a star that has, I don't want to say it's cooled, but I think that's the proper terminology. It has cooled to a point where
exit the traffic circle onto National Business Parkway.
Going on. Like,
in 800 feet, turn right onto Maryland 175 East, Jessup Road.
But it's less intense. So what happened is basically like the star got so big, it had a supernova and ejected a ton of mass, and then you were left.
Turn right onto Maryland 175 East, Jessup Road.
Because it's not as big anymore, the reaction can restart, and it can support with the mass that's there, at least until the star dies again. But those are dwarf stars. They're smaller because they have less mass, because it's been shot out into space as galactic cosmic rays, full circle. And dwarf stars will cool down eventually, and then they won't be able to support the reactions anymore. And then instead of going supernova, because they have so little mass compared to their big brothers, and they won't go black holes either, they just kind of die. Their lights go out. And, I mean, you can theorize what that looks like, but it's probably a big ball of iron in space. We can't really observe it.
Continue on Maryland 175 East for 1 mile.
It doesn't emit radiation like it used to. So, like, if we were tracking a star and the star went out, then it's going to be a black ball against a black void, and there might still be like heat radiating off of it and other things, because we measure more than just light, visible light. But generally speaking, it's going to be a dark object against a dark night sky. Batman approves. Anyway, so that's stars. That's the basics of how they work. Moons are cool. Moons are just planets that orbit other planets. They're just smaller typically. And by typically, I mean they're a lot smaller typically. Like, Earth has a moon that is an exception to this rule. Our moon is ludicrously large.
In a quarter mile, turn right onto Parkside Boulevard.
The moons in the solar system. It's just like ridiculous. Yeah, like the proportions, I mean, are ridiculous. That's what I'm trying to get at. Like if you look at Jupiter, Jupiter's huge, but it has like 50 some moons and counting, or 80 some moons and counting. I think Saturn has like 50 and counting. But yeah, like Jupiter, it's huge, but its moons are small. Or you get something like Mars. Mars has, does Mars have, I think it has 2 moons? I might be wrong on that. I've definitely studied Mars before, and I think it has 2 moons. But don't quote me on that, because I'm in my car, and I can't look stuff up. I'm just going off of memory. Pluto has a massive moon relative to its size.
Turn right onto Parkside
Charon
Boulevard,
is the
then turn
Pluto,
left onto
or
Richmond
the
Stage
moon
Road.
of Pluto, I think. I think it's Charon. Or Charon might be one of Mars' moons. See, now I'm getting this all mixed up. But anyway, its moon is 50% the mass of the planet itself.
Take the next left onto Richmond Stage
Or
Road, then turn right onto Duncannon Lane.
Which is like a quarter of the mass. I'd have to double check again because I am in my car. Regardless though, it's...
Turn right onto Duncannon Lane, then your destination will be on the left.
I'm arriving at my friend's place real quick to go drop something off. So I'm gonna take a
Your destination is on the left.
721. Oh, it's that one. Whoops. Alright, well, where do I park? Yeah. Anyway, I'm gonna pause the recording real quick. Alright, I'm back. That was fast for you guys, but about 45 minutes for me. So, where I left off, if I remember correctly, was talking about space stuff, which is cool. I kind of wanted to shift. So I've been talking about what's in space. I've talked about what space does to humans. I wanted to talk about larger scale, as well as more of like the science that's not science fiction about space travel. So
take the next left onto Richmond Stage Road, then turn right onto Parkside Boulevard.
The universe is absolutely huge.
Take the next right onto Parkside Boulevard.
Like, if you were to... the universe is absolutely huge. Like, if you were to take your mother and lay her on her side, it would be about half as big as her.
In 600 feet, turn left onto Maryland 175 West.
What you got?
Take the next left onto Maryland 175 West.
But yeah, no. All joking aside, the universe is ludicrously big. There are really good videos.
Continue on Maryland 175 West for half a mile.
More justice than I will, explaining how big it is.
There's an 8-minute slowdown on Baltimore-Washington Parkway in 2 miles. You are still on the fastest route.
And I highly, highly, highly recommend looking up a Scale of the Universe video if you want to feel small. But those are really interesting. The universe is really big. We observe the universe in dimensions of light years is what we measured it
in a quarter mile, use the right lane to take the Maryland 295 South Baltimore-Washington Parkway ramp to Washington.
Despite its name is the amount of distance, it's a distance measurement. It's the amount of distance that light travels in a Earth.
Use the right lane to take the Maryland 295 South ramp, then merge onto Maryland 295 South.
Year is just how long it takes to go around the sun or other celestial body of origin. Like something that orbits a black hole still has years, you know. It doesn't have to be a sun. But yeah, so the universe is really large, and it's spread out too. And if you go by how close the closest thing besides our solar system is to us in light years, it's like 4.5 roughly, I think. I think it's either Betelgeuse, the sun, or it's Ceres, but I'm not sure which it is. Whichever one it is, I know it's a red giant, I think. But yeah, it's still like 4.5 light years away, which, if light is traveling at 3 times 10 to the 8th meters per second, which is really fast, and it's doing that, how many seconds are in a year? I don't want to do the math on that, that would be painful, but there is 3,600 seconds in an hour, and multiply that by 24, and then multiply that by 365.25, and you will get the rough estimate for how many seconds are in a year. And which calendars are cool too, in the sense that the year changes length every year by a few seconds. Modern calendars are really good at keeping that number small. And we got things like leap years to help keep things down. And then you got like leap centuries, which are interesting. So like for example, the year 2000 was not just it was a leap year, but it wasn't just a normal leap year. It was like a quad centennial leap year or something. It's like every 400 years, they like do something with leap years to speed it up and slow it down, or they either skip. I think they skip one and then re-add one back in every 400 so years. And 2000 was one of those years. That it was planned out. So that's cool. But that's calendars. That's not space. Space is really spread out. So 4.5 light years away is a really, really far distance. And at its fastest, we can't travel at the speed of light, at least with current technology. And if you want to know why, listen to my podcast on light and how it works. But we can't travel at the speed of light. And even if we could, the fastest we could get there is 4.5 years from now. So, assuming we could get there that fast, you have to keep humans alive in space for 4.5 years. That's a lot of food. That's a lot of water, although you recycle it. That's a lot of medicine you might have to pack if things go wrong. That's a lot of just air and oxygen you need for metabolic processes. It's like, besides the speed issue of trying to go that fast, you have other issues of simply keeping people alive that long. Like, we struggle to keep people alive long enough in space to get them to Mars and back. Getting there, you're pushing your entire lifetime's radiation dosage limit with modern technology, if not already getting cooked. But we can't really get you there and back with modern tech. And that's where I wanted to talk about the science and not the science fiction. I've talked about radiation, how you protect against it already, but I wanted to say that you can scale things up. You can put more plastic in your liner. You can make a thicker hull. You can do everything in your power to make a heavier, denser, stronger, more durable spacecraft. And that's great. It takes a lot to launch that into space, but it's doable. And we probably will do it. What most likely will happen is that'll go up in pieces. If we do make a vessel that goes to Mars and back, recurringly, we'll do it in pieces. That carries humans. So, I know SpaceX's Starship, as of this recording, is planned to go to Mars, and be able to go to Mars in a single super heavy launch. It has enough fuel rating to get there, which is awesome. And also the fact that the fairing payload for that thing is massive. It's insanely big. So the current plan is basically get Starship. I think you do have to refuel it in orbit, but it does have enough onboard fuel capacity to get to Mars. And then you might have to refuel it at Mars too. I'm not sure. If you land it, you definitely do. I'll put it that way. And it also depends on the energy exerted in a capture burn, if you do a capture burn or not. But that's planetary and orbital mechanics, which I could totally talk about. But that's... maybe I will. Maybe I will later, though. Anyway, getting to other stars outside of our own is completely unrealistic in modern technology, and probably will be for many years to come. Unless we invent the warp drive, or natural, wormhole generation that we can control, or any other way to bypass the physics of the universe. If we can do that, we'll be fine. But if you can't break the laws of physics of the universe or bend them to your will, then we probably can't go to another star in any appreciable amount of time. We definitely won't be alive. If those technologies are not invented, we won't be alive when people go to another star. So, get that hope out of your head. Sorry, but it ain't happening. Again, unless we can break the laws of physics. Now, Mars, on the other hand, Mars is much more doable, but I think what we're trying to do is the moon first, and more so again. The moon if you didn't know, we've been to a lot. We were there 50 years ago. I recently, I was picking out gifts for the guys I lead, and I'm getting them different books. And one of them, he studies physics and optics more in particular, but he studies physics. And I have a book that kind of is one of the things that inspired me to be a more STEM-minded individual as a kid. I have a book, I forgot the exact title, but it's like science, like what is going on in the world today, ? And the book was written in 1950. 1950. Like, it's older. The book was written 4 years after my grandfather was born. The book was written way before we went to the moon, if anything. The book was written, like, in the era of we're putting stuff in space for the first time. Like, that's the era the book was written in. So it's a really cool snapshot. It's like 230 pages long. It's a cool snapshot of like what we thought science was going to be like in the future and what we have now, back in the 1950s. And some things they got totally right, and other things are completely blown out of proportion. And I remember I was just thumbing through it yesterday. There's a chapter dedicated to like space travel, and there's a hand drawing, like an artist's rendition of the moon and what it looks like up close, and like what that looks like for us as humans. So this is before JFK announced we're going to the moon. This is before the space race. I mean, it was in swing, but it was before it was in like the full swing that it really was, in the 60s and late 50s. Like, the book captures what space travel and other sciences they thought would be like. And like I said, some things it's accurate, some things it's not. And that was 70 years ago. So, all that being said, if a book written 73 years ago, can more or less accurately describe within reason what modern science is going to be like, even though there's not like I guess they have microprocessors, but like modern technology in any shape and form, like the computer didn't really exist back then. Maybe in like a lab somewhere people were messing with computers. I mean, I know some origins of like the IBM and such. They had IBMs back then, but they took up entire rooms and used punch cards as inputs instead of keyboards. Like, if those people in such, I don't want to say archaic, but it's such non-advanced technology as we have today can dream up semi-accurately what we would have today, then I think I can, even from my viewpoint, can semi-accurately say that in 70 years from now, by the time I'm dead, if I live to be that age, like, we wouldn't have gone to another star with the current technology we have and the rate of technological growth. Like, I don't think that would have occurred. Now, 200 years from now, I can't make an accurate estimate about. But 70 years from now, I can make a good guess. So, that's kind of what I'm getting at. And I'm giving that as a gift to my friend that I lead. And I think it will be a good grounding rod for him, I hope. And I do, like, it was a book that shaped a bit of my childhood, so I do care about it. Like, I'm a little sad and to give this away, but I'm more so happy that I can share it with him. You know, it's not like I'm going to find another copy. The thing was written in 1950. You know, maybe in a library, in an ancient library somewhere. But, yeah. Actually, I'm driving. It's in a bag next to me in my car. I'm in traffic, but I'm not planning on pulling it out. That's why this podcast is also going so long. It's 45 minutes to get to my friend's place, 45 minutes to stay there, 45 minutes to head back, and then I got about 45 minutes once I'm home to get to community group tonight. So it's all in chunks. It's all in chunks. And I've had a long day, a long couple days, but I'm excited. I'm excited to hang out tonight with them. Anyway, back to space. I don't want to spoil the plot of Portal 2, but space is how it ends. Okay, side tangent. In Portal and Portal 2, the white walls that you shoot the portal gun onto are made up of crushed up moon rocks. And Cave Johnson mentions that in his monologues throughout the game, that the reason Aperture Science went run down and ran out of money was because they were buying moon rocks and using them, and they ran out of money buying moon rocks because the space program shut down, or the lunar program shut down, and they went bankrupt. So even in that, it's a commentary and a joke that, like, oh, the stuff on the moon is so alien and ancient and also archaic and eldritch to us. I'm just throwing a bunch of vowel-sounding words that describe space together. It's so ominous that we can build portal guns and use moon rocks. Like, that's science fiction, you know. Science fact is the moon, the lunar regolith, is a mix of a couple things. It is, I know, an aluminum oxide dust, as well as silicon oxides. There are other heavier metals. I think there's nickel and some small trace amounts of iron on the moon. And I'm trying to think if there's anything else besides aluminum, silicon, nickel, iron, and other little trace amounts. Those are the main things, I think. And let's see, quartz is made of silicon. So yeah, I mean, the moon is made of dust, and it's not like densely packed dust. It's like pretty loosely packed dust. That's why when stuff hits the moon, it really makes like big dust clouds, explosions. I have another friend who is currently dating the friend who does the Isaac volcanoes research. This friend does cloud or dust vector analysis on things like moons and the moon. So he analyzes, like, when something impacts the moon, how does the dust scatter? How can we measure that? So that I can develop a model for reverse engineering what impacts look like. So if you know what the dust cloud looks like, then you know what hit the moon at what speed and what angle, and how big it was. So that's the research he's doing. He has a PhD from Oxford University over in England. He's a brilliant dude. And I'll see him tonight, hopefully. Although I think he was flying out to San Francisco for a trip. Maybe it's Florida. Anyway, work trip. Anyway, the moon is made of dust. And so, that dust, it contains some pretty useful stuff. You're not going to find, like, water, because I don't think there's many hydrogen anythings up there, or hydrocarbons, to melt down and burn to make water. But you got plenty of oxygen. You just got to burn stuff to make it. And the other stuff you're left with are super useful. So, aluminum is basically what spacecraft are made of. And you can make buildings out of aluminum. You can make not tin cans, what am I saying? Aluminum cans out of aluminum. You can, just anything that's metal, you can usually shape out of aluminum. Or aluminium, as my friend Raman would say. But he says it as it's spelled, and it's spelled differently here in the U.S. They have an extra vowel in it, than compared to what we have. But yeah, so you melt down aluminum oxide, and you get aluminum, and you get oxygen, and you can breathe. Yay. You get also super useful aluminum. Now, if you melt down like silica oxides and other things, you get oxygen. You get quartz, which is crystal. You can use that in optics. But you also get the stuff used to make semiconductors, so electronics, as well as like silicon, which I think actually silicone, the stuff you use in cooking, I think that's a mix of petroleum with silicon, silica. I'm not quite sure, but I know it's not just plain old silicon. But yeah, you get stuff to make, semiconductors, and other trace elements you can use for other trace things. So the moon, if you're going to live there, you can bring your own tanks, and you can bring stuff, and there's only so much you can recycle. You can use the Sabatier process to break down your carbon dioxide you're exhaling back into oxygen. But it also makes a really powdery, fine carbon, like dust that gets everywhere, and if it gets on electronics, it'll short it. I know these random little technical tidbits about things. Like carbon dust is bad for electronics. They teach you that in aerospace major when you're on space track, because you talk about different ways to purge CO2 from your cabin atmosphere. You can use lithium hydroxide canisters that just suck the stuff up and absorbs it up to a limit. That's when when Apollo 13 had its bad accident, where one of the oxygen tanks blew up and they were losing pressure. Their CO2 levels were also building, and the big old fix that they used the duct tape for was to fit a round peg in a square hole, or vice versa. It should be a round peg in a square hole, because lithium hydroxide canisters are usually cylinders, and they basically had their CO2 system was busted, so they had to use these short-term limited use canisters, but they didn't fit. Which now all that stuff's standardized. We learned from Apollo 13, but to make it fit, they used duct tape. So, more you know. Which that whole thing. I've never seen the movie Apollo 13, by the way. Despite being an aerospace engineer, I've been saving it as a sweet treat, but I haven't seen it yet. This is just stuff I know from history. I also learned yesterday that you can fit a round peg in a square hole. You just gotta turn it sideways. Because if you think about it, the cross-section of a cylinder on its side, not on the circular face, but on the rounded cylindrical face, is a square, if you look at it from a flat perspective, 2D perspective. You also can fit that, of course, in a round hole, too, because it's rounded on one side. So, if you can't fit a square peg in a round hole, you just need to cut your peg so that it makes a square. That its diameter is equal to its height. And if you can do that, you can fit a round peg in a square hole. So, fun fact. Anyway, lunar dust is useful. And I don't want to say a lot of what I pulled this info from is, I don't know if you've ever heard of Artemis, but Artemis is several things. It's a NASA project for going back to the moon, but it's also a book by the same guy who wrote The Martian. Was that Andy Weir, I think? He writes a book called Artemis, which takes place in 2088, where we have a big lunar colony, and that colony has 10,000 people on it who live there more or less permanently. And how they support that colony for the oxygen it needs is they have big smelters a couple miles away from the colony that smelt up the lunar regolith, the dust, and makes aluminum, and they make oxygen from it, and they have a nuclear reactor up there. And they use the aluminum to build the colony. Like, it's cool. And they built an outer shell and an inner shell, and there's a 3-foot gap between the outer and inner shell, and in that gap they put lunar regolith. They put dirt, and that's to protect against galactic cosmic rays. Full circle. So even that science fiction writer was able to pretty accurately do his research to write accurately enough that a realistic colony base on the moon in 2088 would have these things. It would have walls thick enough, if it's not underground, thick enough to block GCRs. It would have its own oxygen production, and it would have a way to make materials in situ or in mission, so that it didn't have to bring stuff from Earth, because that gets expensive. Yeah. I also like in that one, it's the Kenyan Space Agency runs it all, because Kenya's on the equator. So they like, oh, we have the best place to launch to the moon. So they capitalize on that. I find that funny. And cool. I just wish Ecuador had a space program, because they're also on the equator. And when I went to Ecuador 5 years ago, to study abroad a bit, and I did ask them, I was like, hey, do you guys do anything with space whatsoever? And by them, I meant I was in a government building talking to a policymaker as part of the field trip, and so it's his job to like know what's going on, and he was the energy policymaker, I believe. So he was managing like the power grid for the 3 largest cities in Ecuador or so. And I asked him like, hey, does Ecuador have any space program or any, if not, like any interest or investment in space technology? And he said no. So Ecuador doesn't have a space program, as far as I'm aware, as of this recording, as of 5 years ago, where I heard the info. So, yeah, but if you are listening to this entire podcast and you, for some reason, refer to yourself as a whole country, get a space program. Anyway, so that's the moon. Mars is practical. Let's go to Mars next. Which, by the way, we're going to the moon first to test technology to go to Mars. That's the main goal. Because if we can live long-term in space on the moon, we can definitely live long-term in space on Mars. Mars actually has an atmosphere. It's 1/30th the thickness of our atmosphere, but it has an atmosphere. And in that atmosphere is mainly carbon dioxide. But from carbon dioxide, you can make breathable oxygen. You just gotta pump and dump a ton of energy into it, which you can get from solar panels, nuclear reactors, all sorts of stuff. Yeah. So, Mars is more habitable, but it's also less in some ways too. Being farther from the sun, you do get less radiation to the planet. So it's still a concern, but it's a little bit less than the moon. You'll get fried in a few seconds on the moon. But yeah, Mars is terrain, its ground is primarily iron oxide. So that's why Mars is orange, as it's the color of rust. Rust is iron oxide. I believe it's F2O3, or the other way around. It might be F3O2, but I'm pretty sure it's F2O3, Fe2O3. And so the ground is made of iron and oxygen. So you smelt that up, you now have iron and you now have oxygen, and you can build stuff and breathe stuff. And the other good thing about oxygen is it's a catalyst, or I don't know if catalyst is the right word. It's one of the necessary things needed for combustion. So if you can find a viable fuel source on Mars, then you can actually have fire. And anytime you can have fire in any situation, you can have a civilization. Pretty much. Like, that is the root of civilization, is burning stuff. Because if you can burn stuff, you can build stuff. You can cook stuff. You can make stuff. You can invent stuff. You can be warm enough, too, as well. Because Mars is pretty cold. Actually, on its equator, Mars gets about 80 degrees Fahrenheit at peak hours, which is nice. But in the cold times, you're looking at like negative 140 Fahrenheit, or in the poles, like negative 260 Fahrenheit, I believe, off the top of my head. It gets really cold there. So heat management is a big thing on these kind of extraterrestrial bodies, on top of radiation and water and all the other things you have to manage. If you've ever seen The Martian or read the book, they do a good job of explaining it. And I think they do a pretty accurate job of like what it could be. So like if The Martian, I can't remember if they give a date, like a year of when all the events happen, but if you told me that occurred in 2040, I would believe it. Like, we definitely would have the technology as well as the capabilities and probably the funding to do what they did in The Martian, by 2040. That's my hope and guess. Seeing how by the end of this century, or decade, sorry, the end of this decade, we're going back to the moon in full swing, is the plan. I'm sure we can go to Mars by the end of the next one. Yeah. So there are other planets, though, besides Mars. Mars just is the shortest to get to. Shortest to get to that's worth for humans to go to. It takes between, 18 months and 2.5 years, I think. Maybe 22 months. Not 22, 26 months? Something like that. Depends on your launch profiles, and you can always look up pork chop plots to figure that out. If you don't know what a pork chop plot is, look it up. It's a pretty cool plot. You're going to look at it, you're going to realize you have no idea how to read it, and then you're going to, be sad. But let me tell you, it's a heat plot of potential energy costs to go distances. So pork chop plots are really great at measuring how much energy you need to get from point A to point B. There's a game I play called Kerbal Space Program that I've been playing for 10 years at this point. I have several hundred hours in it. And I have a mod that lets me generate pork chop plots and plan out rendezvous and orbital maneuvers to get from one orbit to another. And those are cool because I know how to read them now. I didn't know how to, 5 years ago, but now I do. And they're awesome. They basically show hills and valleys of potential energy. So it might look like a bunch of circles, concentric circles and ovals orbiting something. And along those circles or lines, you'll have numbers, and that's the energy value it takes if you were to launch at that time and day, or did a maneuver at that time and day. So the axes are usually arrival time and leaving time, departure time. And then what's in the circle is the energy value. So they're pretty useful. They're non-intuitive, but they are cool for mapping out space travel. So that's less science fiction and more science fact there. I hope you appreciate that. I've been talking for an hour and a half straight. My voice is getting tired. What else can I talk about and be brief? I think I can talk about other planets, but they're just not as interesting as the moon and Mars. Venus is pretty cool. Venus is hot. Its atmosphere is so thick it just traps in the heat from the sun. And Venus is hotter than Mercury, even though Mercury is closer to the sun, because Venus has a much, much, much thicker atmosphere. I don't know if Mercury has an atmosphere, actually. It might be like the moon in that respect. I have to double check. But Venus has a really thick atmosphere. And the greenhouse effect, greenhouse gases, they work. They make the Earth hotter. They make Venus hot. Although Venus is interesting because the planet rotates really slowly. I think, and again, don't quote me on this, but I know I'm pretty sure its rotational period it's either between 80 and 120 days or something. Or maybe it's 200. It's almost as long as its year. So you get this phenomenon where one side of Venus is boiling hot and the other side of Venus is frigid because it hasn't seen sunlight. And because there's a great temperature difference and the atmosphere is so thick, you get these huge, tidal currents of just convective air currents of air in the atmosphere just swooping around, making huge storms, heat storms. It's pretty interesting. There was some years ago, I think both the U.S. and Russia have now sent spacecraft into Venus's orbit, and then also crashed through the atmosphere. I'm not sure. I think one of them actually made it to the bottom and landed and sent data back. I'd have to double check that because the atmosphere of Venus is so thick, so hot, and there's so much ionization going on, you can't really get a signal up, is the problem. But I think
in 2 miles, take the exit toward Maryland 410 West Riverdale Road.
I want to read about that. But yeah, so exploring Venus is kind of a no-no. It's thick, it's toxic, it's hard to get to. Science fiction. Mercury is really close to the sun. There's too much radiation for probably biological life, even though it's not as hot. There's other things that will kill you. Probably not practical. Once you get out of Mars, the closest thing is Jupiter. And Jupiter is, it's a gas giant. We're not going into a gas giant. That's dumb. They're really hot, and just for the same reasons, they have huge convective currents, and there's not anything to land on for a while, as far as we know. You don't want to go to a gas giant, but you might go to its moons. So, there are moons that orbit Jupiter, like how we orbit the sun, that are useful and cool. So you got moons like ice volcanoes, although I think that's methane ice. I know right now they're exploring to see if one moon has water on it, either ice or liquid, and it might be in its own little version of the Goldilocks zone, but I don't think it is. I think it is ice, frozen water. But you could have, liquid water on something. That'd be cool too. You gotta check the moons, man. You don't ever know what you'll find. Like, there's 9, if you count Pluto, planets in the solar system, and we know some things about the 9 planets. But the fact that Jupiter has like 80 moons and counting, like you almost did 10 times your number. And like things you can explore that you can land on or go near. Like, that's cool. You gotta check out the moons. And honestly, when it comes to real estate, you're not gonna use it all up.
In a quarter mile, take the exit toward Maryland 410 West Riverdale Road.
Yeah. But anyway, and once you go past that, like, Jupiter, Saturn, Uranus, Neptune, that kind of stuff, Pluto, they're just more, with the exception of Pluto.
Take the exit toward Maryland 410 West.
It's actually kind of theorized that Uranus has a diamond core. I've heard that theory before.
In 1,000 feet, turn right onto Maryland 410 West Riverdale Road.
To confirm that, but that'd be cool if it's all diamonds down there. But yeah, Pluto would be interesting to go to, but it's just a giant. It's a giant meteor.
Turn right onto Maryland 410 West Riverdale Road.
Meteorites are landed. Meteors are like in the atmosphere traveling. Meteoroids are in space, outer space, I believe. So, but yeah, Pluto's just like a big meteoroid. It's not probably as solid as we'd hope it to be, sadly. Anyway, that's Pluto. There is another dwarf planet in orbit of the sun. It is like the size of a moon, not our moon, but a moon.
Continue on Maryland 410 West for 2 miles.
But it is cool. Look it up if you're interested. Anyway, I'm getting long-winded. My voice is starting to hurt, and I've really enjoyed doing this podcast today. It's kept me busy, but also, like, this is my passion. This is like my hobby. This is what I studied for 5 years and played 10 years of video games around. I like space. I like outer space. I like things that go into space. I like the things that are in space, and I like it when humans try to go in space. That's probably my favorite. Like I said, I studied life support and human factors. It was my specialty, both on my capstone team and in my studies. And I do HVAC now. So, I'm doing life support just on a more ubiquitous scale than space travel, which I'm fine with. I'm happy with that decision. And it pays better than aerospace does. But anyway, I hope you enjoyed this podcast about space, what's in it. I know I did. And I will see you. Well, I hope I never see you. That would be creepy. But I hope you will hear from me again soon. And then I'll hear you from you soon. Thanks for watching and listening, and I hope the background content, whatever it is, was interesting as well. I have a lot of fun, like, recording YouTube videos and just speeding them up. Or recording screen capture game footage and speeding them up. try and make them fit. I know I've done Starbase, I've done World of Warcraft so far. I don't know what I'll do next. Maybe this one will have something different. I don't know. But anyway, thanks for listening. Yeah, let's call it here.